Segments and congruence. In geometry, a rule that is accepted without proof is called a postulate, or sometimes called an axiom. However, in my class, I will be referring to it as a postulate. Up first, we got the ruler postulate, which says that points on a line can be assigned numbers corresponding to a number line, in that the distance between the points is the absolute value of the difference between the assigned values. That's a pretty heavy description of something that basically is talking about this instrument here, a ruler. All right, so if we got, let's do a breakdown here. If we got 2 points that sit on a line, okay, so we got point A and B that sit on a line, which that line could be horizontal, it could be vertical, it could be at a diagonal, or whatever the case. The A and the B could also be flipped in different spots, but they're just 2 points that are sitting on a line. What you can do is you can put a number line on top of that line, and it can move around. It doesn't have to, you know, if you're thinking about a ruler, you might really be thinking, we'll start at 0 and measure over, right? And that'd be a smart idea to do, but you can put any type of a number line, such as a ruler, along that, and you can assign each of those points a location. So I could let A be 4, B, that might be like 7.5. That's a little bit hard to tell with all lines, but it might be 7.5. And if I take the difference between those two values, whether I do 7.5 minus 4 or 4 minus 7.5, and take the difference that I get, which would be 3 or negative 3.5, or sorry, would be 3.5 or negative 3.5. If you take the absolute value of that, you get 3.5, and that would be the distance between the points. Okay, and that's the ruler postulate. In example number 1, we're going to use the ruler postulate to figure out the distance between certain points. So what we have here is a picture of a number line that's got values all the way from negative 7 to 7. We've also got some points that have been identified. We got J, K, L, and M. Okay, and then we've got 4 problems to work on here. What you're going to notice in each of these is there's not a lot of information that's said. It's just like 2 letters, J, K, J, L, and so on. Okay, but when you have 2 letters that are just side by side like that, that represent points, whether those points be on a number line or in some other like type of a diagram that we've got, if you've got 2 letters that are side by side with each other, you're supposed to read that as the distance from J to K. Okay, so this is worth some value. It's going to be equal to something, the distance from J to K. Okay, so all we got to do is go look for these numbers that, go look for these points that would be on the number line. Here's J and here's K, and you count the space that would be between them, right? You've got 1 unit here, 2 units, you got 3 units. So JK is equal to 3. Now you can get very technical if you want and grab the actual numbers and subtract them. If you took negative 6 and you subtract negative 3, that's the same thing as negative 6 plus 3, which gives you negative 3, and then the absolute value, we'll talk about that here, the absolute value, negative 3, would be 3. But it's really just the space that's between it, so don't need to make it too complicated. J to L. From J to L, we've got, well, we already know 3 to K, so we got 4, 5, 6, 7. So that would be equal to 7. JM, that would already be to 7 here, and then going to M, we're going to have 8, 9, 10, 11, 12. That'd be 12. And if you're not building off of the others, the way you can do it is just say, look, here's 0. From 0 to negative 6 is 6. 0 to 6 is 6. 6 plus 6 is 12. All right, and then KM, negative 3 to 0 is going to be 3, and then 3 to 6 is, 0 to 6 is 6. So you got 3 and 6, which will give you 9. And that is the ruler postulate. Put a lot of points that are on a line, like put a number line on top of it, and just match things up. Our second postulate is going to be the segment addition postulate. And what it says is that if you got 3 points, A, B, and C, that are collinear, that means that they're in a straight line. That's important here. If you got these 3 points that are in a straight line, and B is between points A and C, then the distance from A to B plus the distance from B to C would be equal to something. Well, let's go ahead and draw a picture. You might already know the answer, but let's go ahead and sketch a picture real quick just so that it's clear. All right, so we got A, B, and C, and B is going to be between A and C. That means that A and C will be the endpoints. And B can be anywhere along here. It doesn't need to be directly in the middle of them, but B is somewhere between them. All right, and our postulate says that If you take the distance from A to B, which is the length of that segment there, if you take that one and you add it to the distance from B to C, that would be equivalent to, well, that segment and this segment together, the distance all the way from A to C. So it'd be equal to AC. Now, it's really important that we go back to the word collinear and make sure that we understand that that's part of the situation that we have here. So collinear means that these are in a straight line. So when you put these two segments together, you're still getting a straight line from A to C. But if you had the points not collinear to each other, if you had A like this, there's B, there's C, okay, you can't take the length of that segment plus the length of that segment and say that it would be the same thing as this segment here. In fact, AC would be less than the sum of AB and BC. So it is important that we're looking at this being collinear. In example number 2, we're going to do a basic application of the segment addition postulate. All right, so what we got is a line. It's got 3 points F, G, and H on it. The distance from F to H is going to be 36. The distance from F to G is going to be 21. We're asked to figure out the distance from G to H to figure out what that is there. Well, if the two small parts have to add to give you the full distance, being that they're collinear in the picture here, you can just take the 36, subtract the 21, which will give you 15. And that's it. All right, so here's where we get into the somewhat confusing things, a little bit with vocabulary and how you have to use certain words versus other words. Okay, we got congruent segments. Congruent segments are segments with the same length. You might want to say that that means that congruent segments are equal to each other. Okay, if they have the same length, then they're equal to each other. But the thing that we got to be really careful of here in geometry is that we don't mix the word congruent with the word equal. In a way, they're kind of the same thing, but they're also different. The word congruent is more about shapes. Shapes that would be the same size, or like segments that would be the same size, are called congruent. The length of the segments, the size of the shapes, anything that could be quantified as a number would be things that we can say are equal to each other. Okay, so numbers can be equal, but shapes cannot. Shapes are going to be congruent if they're the same size. Okay, in the box here, we've got two segments. We got segment AB, we got segment CD. Okay, I want you to take note of the little, that's called a marking. It's just a little slash that goes through that. Okay, and now each of these has one marking on it. You can do 2 markings, you can do 3 markings, and you'll see that in other pictures later on. But these have what we call a single marking on it. That single marking is indicating to us that these two segments are the same size, that they are congruent to each other. Now that they are congruent to each other, there's 2 different statements that we can write. Okay, let me skip over to this one because I'm using the word congruent right now. Okay, to say that these segments are congruent, you actually have to write it as line segment AB, so you get the little bar on top of that. You can say line segment AB is congruent to line segment CD. The congruent symbol is going to look sort of like the equal sign, except that it also has that little wavy part that's on top of it, and that's the congruent symbol. So if you got 2 shapes that you want to describe as being the same size, you can use the word, or you can use the symbol congruent between them. Now, if we specifically want to talk about the length of them, okay, first, you're going to drop that little bar off that you have above the A and B. Okay, you're going to change it from reading as line segment AB, which is a shape, to just as AB, which refers to the distance from A to B. And the distance is going to be a number. Okay, so we want to say that the distance from A to B is equal to the distance from C to D. So we're using equal signs for things that refer to numbers, but we're using the congruent symbol for things that are referring to shapes. In example 3, we're going to plot 4 points so that we can make 2 segments. We're then going to look at those segments and determine whether or not they are congruent. If they are congruent, we'll go ahead and write a congruent statement for those as well. All right, so point J, let's see what we're going to be connecting. All right, J is going to connect to K, so I'll do those in one color. We got -6, 4. It's 3, 6, and 4. Okay, so that's J, and then K is at -1 and 4. All right, so that's going to be really convenient because they're at the same height there. So JK definitely has a length of 1, 2, 3, 4, 5. It has a length of 5 units. All right, let's see what LM is going to look like. L is at 1, 3, and M, where is M at? There's M is at 4, 7, so we're at 4, 3, 7, so it's going to be up here. All right, so LM's different because that one's at an angle there. All right, are they the same size? Well, do they look like they could be? A little bit. They appear as though they could be the same size. So they appear to be the same size, or look like they might be close enough to the same size. What I'm going to do first is just take a little piece of paper that I have here and take a measurement of one segment and do a comparison to the other one, right? So I know that this is 5 units. That's easy enough, right? Because we already counted 5 units, but I'm going to mark it on the paper. So I'm going to measure from that corner out to there, and that's JK. And now if I take that over to here, that does look pretty solid. Looks like that's going to be 5 units as well there. Now, is there any way that we can verify that for sure? Well, we looked at this with the distance formula previously. You can make a right triangle that uses LM as the hypotenuse, and when you do that, you can then apply Pythagorean theorem. So if we look, that's easy to count 3. That's a difference of 4, and this actually ends up being when your Pythagorean triples, 3, 4, 5, which we can still verify to decide if you didn't know that was a triple. We'll take 3 squared plus 4 squared. That would be 9 plus 16, which is 25, and the square root of 25 is 5. So yes, JK is congruent to LM, and we could write this statement. Actually, we're going to write 2 statements. We're going to write that JK, line segment JK, is congruent to line segment LM. We're going to write that, and then we're also going to write another statement about their lengths. We could say that JK is equal to LM, and that's because they're both equal to 5.
Wait, there was.